In chapter 28, we talk about reflection and refraction, both of which are responsible for lots of the things we see and how we see them. Anytime you have light that shines on a surface, here's a surface. There's a couple of things that can happen. The light can be reflected. We call this an incident ray. This would be reflected. So one possibility is that the light is reflected. Another part is that it will actually go into the medium. It goes into the medium. Let me make that a little more obvious. It often appears to be bent. When it enters a transparent medium, we say it's been refracted. And the third possibility, which is harder to draw, is that the light energy can actually be absorbed. Generally, some combination of these happen. If the material is opaque, something solid like a shoe, we will see the brown light reflected and the other colors of light will be absorbed, and we won't see those. If the object is transparent like a piece of glass, what we'll often see is that some of the light will be reflected and some of the light will be transmitted. And that transmitted light is bent. We call that refraction. So if this was a pane of glass, we'd have light coming in, some would reflect off, and some would pass through. Notice the light bends again every time it changes, as it goes from air to glass, back to air. We'll come back and we'll talk a lot about refraction later. We're going to start with really talking about reflection. The first thing we want to know about reflection is something really simple called the law of reflection. The law of reflection just says and this is true not only for light, but for all waves, that if we draw a normal segment, that means a perpendicular line there. That's how we measure the angle. That would be the angle of incidence, the angle the light rays coming in. And this would be the angle of reflection. And the law of reflection simply says that the angle of incidence is equal to the angle of reflection. So, if this incident angle right here is 38 degrees, then this reflected angle right here is 38 degrees, and that distance from here to here would be 76 degrees. It'd just be the sum of those two angles. One of the interesting things is using this law of reflection, we can actually see how plane mirrors, and the word plane in this case just simply means flat. A flat mirror, like your bathroom mirror, makes images. So, draw a picture. Here's a mirror. And we'll put an object in front of that mirror. The easiest thing to do is put something that has a little direction. So I'm going to put an arrow in front of that mirror. And if we just look at the tip of the mirror, of the arrow, the tip of the arrow is going to send out light waves in all directions because the light will reflect generally in all directions. So we'll just draw a few. So you might have a ray that's coming perpendicular like this. Well, a ray that's coming like this, that hits at 90 degrees, will simply come in and go out at the same angle. So it'll come out like that, it went in like that. But if you have a ray that comes in like this, it's going to bounce off at an equal angle. Like that. That's that law of reflection. Or if you have a ray that leaves the tip and it's coming in at some angle like this, it too is going to follow that same law and go off like this. So what we see is the rays that are reflecting off the mirror seem to be spreading out. They're diverging. They're going off like this and like this and like this. If you're over here trying to see something, there's your eye. You're looking at things. You go, oh my goodness, what do I see? Well, your brain is really clever. What your brain does is it sees this ray coming from back here. And it sees this ray coming from back here. And it sees this ray coming from back here. It traces these rays back, and it says, oh, the tip of the arrow is right here. And if we did that for every point on that arrow, we'd get an image that looked like that. Flat mirrors are really interesting because they provide something called a virtual image. The reason it's called a virtual image is because there's no light that's actually back here behind this mirror. It just looks to your eye as if these light rays are coming. These light rays here appear to come back from back here, but they're not really there. Playing with mirrors form images that are the exact same size as the original. I probably didn't draw them the exact same size, but they are. And they are the same distance behind the mirror, or they appear to be that far behind the mirror, as the object is in front of the mirror. So in this case, if this object was 18 inches in front of the mirror, the image would look like it was 18 inches behind the mirror. The distance from here to here would be 36 inches. Okay. Now, flat mirrors are certainly not the only type of mirror. They're really the very simplest to understand, and they work completely because of the law of reflection. But there are mirrors that are curved. The most common curved type of mirrors are called spherical mirrors. And they may look like this. That's one that's caved in. Well, I don't want to get complicated with forming images, but it's as if we have a lot of little bitty plane mirrors. So if you have light that comes in and hits right here, it's going to come straight back. But if you had a light ray that hit right there, it's coming straight back would look like this. Okay? Bottom line is, and that's a concave mirror. We also have some that are convex. We're not going to go into the particulars of concave and convex mirrors, but I do want you to understand that they follow the law of reflection. They act as if these are a lot of little bitty flat mirrors. The result, though, is they can form images that are larger or smaller. Magnifying glass, your makeup mirror is slightly concave, like that. But all your funhouse mirrors, they can cause distortion. So you may appear in a mirror to be closer or farther or larger or smaller, and we're not going to worry about that. This type of mirror can also form what we call a real image. In other words, instead of having a picture behind the mirror, you can actually put a screen out here, like a movie screen, and it could form a real image, which means the light actually is reaching that point. The back of your eye, the retina of your eye, is kind of like a movie screen, and that has real images that form on it because the light actually makes real pictures on your retina. Okay, so if a light is actually converging to make the image, we call that a real image. If it just looks like there's something behind the mirror, like in our bathroom mirror, That's called a virtual image. Now, this whiteboard looks white because all the colors of the spectrum are reflected. It reflects light, but it doesn't let me see myself like a picture like I can in my bathroom mirror. Okay? What we find is, depending on how smooth something is or how rough something is, determines whether or not we can actually create or make images. So, for example, most things, if you look at them closely, are somewhat rough if we were to examine them under a microscope. And when you have something that's rough, we get something called diffuse reflection. In diffuse reflection, if I send a bunch of light rays that are all going in the same direction, all in the same direction means they're nice and parallel. Well, depending on where they strike this rough surface, they can go flying off. That one may go that way, and this one may go this way, and this one may go this way. But we won't be able to form a nice, clear image. Okay. This whiteboard, even though it feels pretty smooth to the touch, has diffuse reflection. It sends the light scattering in all directions, and it doesn't make a clear image. Now, on the other hand, if a surface is very smooth or very polished, we get something called specular reflection. I'm not sure your book even uses the word specular reflection, but they talk about a polished surface. Specular reflection allows you to have a surface smooth enough that if you had a bunch of parallel light rays, they would in fact all reflect parallel. Specular reflection is what allows us to form clear images. So that brings up the question, well, how smooth is smooth enough? Because this can't be perfect. Nothing really is. Well, the rule is something is polished is if the rough bumps, let's exaggerate this again, here's our rough bumps. If these little bumps between here and here are smaller than 1/8 of the wavelength. Well, so in other words, it depends on what you're talking about. If you have a radio wave, and it has a wavelength of 10, well, let's make it easy on ourselves, 8 meters, then you're polished if your rough spots are only about 1 meter apart. You can actually be pretty rough. Okay? However, if you are a light wave like red light, which might have a wavelength of 750 nanometers, then if you want to be polished, then you would need those peaks to only be maybe 100 nanometers apart. Okay, so how rough or smooth something really is makes all the difference. See if I've talked about everything I want to talk about reflection. I think so. So let's go back to this idea of refraction. Okay. Refraction really just means the bending of light. But refraction happens when light enters a transparent medium, or when it travels from one transparent medium to another. And we've all seen this. We've all had maybe a drinking straw that was in a glass, and you look and it looks like the drinking straw is bent, but you know the drinking straw is not bent when you take it out. What's going on? Well, it's not the straw that's bent. It's the ray of light that's coming from the straw that actually bends. If we have a situation here where we have air up here and water down here, I kind of drew that bend, I didn't mean to. If light enters at this angle here, it's going to bend. This is called the angle of incidence. This is called the angle of refraction. And you can see those are two different angles. Generally, it depends on whether or not light is speeding up or whether the light is slowing down. When light slows down, it bends towards the normal. So in this case, it was traveling faster. When it entered the water, it slowed down. Now, I can give you a little explanation of why that might happen. If we think about pushing a baby buggy that has wheels, there's a wheel here and a wheel here. This wheel hits the water first. Only let's think about this as being a hard surface like concrete and a slow surface like sand or gravel. If you're pushing something along, you're pushing the baby buggy along, and this wheel falls off the pavement first into the gravel, it slows down the most. This wheel will continue to go faster, and the result is the baby buggy wants to turn this way, causes the light to bend. Okay. It also has to do with Fermat's principle that says light is going to travel the quickest path possible. It's a little harder to see why bending would make it faster unless we put in a second surface. If for some reason, and I know we can't have water that looks like that, but we'll pretend that we could, an air, water, air surface, it wants to travel, since it travels slower in water, it wants to take a really short path in water, and it will take a longer path back again in the air. Okay, I probably confused that more than necessary. Let's just back up and go back to the beginning. When light slows down, it refracts or it bends toward the normal. If light speeds up, it's going to bend away from the normal. So let's think about, let's have air. It travels very fast in air. And then we'll have glass. And then we'll have water. Well, let's think about how fast light travels. In air, it travels at about c. That's 3 times 10 to the 8th meters per second. It's not noticeably slower than light in a vacuum. It is slower, but it's a very small amount slower. In glass, it's going to travel at maybe 0.67 c, about 2/3 the speed. So it's going to definitely slow down. Water, it's going to travel at about 0.75 c. So definitely slower in water, but it does travel faster in water than it does in glass. And the reason, of course, is the molecules in glass are packed a little closer together. So all that absorbing of photons and emitting of photons just slows down more than it does in water. So if I have a beam of light, let's get a beam of light. I have a nice red beam. It's coming in at a pretty big angle. Well, here's the normal at that point. It's going to bend toward the normal because it slows down. When it leaves, it's going to bend away from the normal because it's speeding back up, but not back to its original angle because it's not going to speed up as much as it was in air. If it went air, glass, air, it would actually come at the same angle as it was before. If we were to have our light travel the opposite direction, if we started coming in at this angle, it would still follow the exact same path. If it went from water to glass, it would slow down and it would bend toward the normal. And then when it went from glass to air, it would speed up and it would bend away from the normal. So it's this difference in speed that makes things appear the way they are. Now, one of the things that we talk about and that we do is we really do want to measure, well, how fast or how slow are different transparent mediums. So we have a way of rating how fast or how slow these transparent mediums are. And we use something called the index of refraction. And the index of refraction is represented with just a lowercase n. And n is equal to the speed of light in a vacuum divided by the speed in the material. For example, they know for water, well, the speed of light in a vacuum is 3 times 10 to the 8th meters per second. And in water, it only travels 2.25 times 10 to the 8th meters per second. That comes out to be about 1.33. I think that's right. I'm going to double check my math because I'm a big believer. 3 divided by 2.25. 1.33. Notice it doesn't have any units because the units completely cancel out. Okay. Also notice it's bigger than 1. It's always going to be bigger than 1 because the speed of light in a vacuum is always faster. Generally speaking, the larger the index, the slower the material. So water is 1.33. Glass varies, but it might be 1.5 to 1.6. It just depends. A diamond is about 2.4. A diamond is probably the most optically dense material that you guys are familiar with. It slows light down the most. Right? Eyeglasses, if you go to buy eyeglasses, they use different types of materials. In my case, my glasses are very thin and light. They use something called a high index material. And by using the higher index, it allows you to have thinner glasses because it slows down the light more. It can do more refraction in a thinner lens. I don't need as thick a lens to accomplish what they need to accomplish because the index makes them bend even more. One of the things that happens because of refraction are these optical illusions. The classic is something underwater. If I have a fish underwater, here's a little fish, and I have a little ray of light that leaves the tip of the fish's nose and travels up. When it reaches the air, it refracts away from the normal. So somebody over here trying to catch the little fish thinks the little fish is right about there. Of course, he's not. So it helps to know your physics if you're trying to catch fish. Notice he also appears like he's closer to the surface of the water than he actually is. Another thing that happens is we actually don't see the sun where the sun is. If this is the Earth, and you're right here, and I do it kind of exaggerated, you would probably think you couldn't see the sun when it's down here. But because the light from the sun refracts, it kind of bends like this, you tend to follow it out here. You think the sun's there. So one of the things that happens is you see the sun after it sets. That may seem weird, where it's actually below the horizon. But because of the light that it gives off, you think it's still above the horizon. You also see the sun before it rises. So if you think about it, we don't have 12-hour days and 12-hour nights. You actually see the sun for more than 12 hours each day. And that's because of refraction. Okay. One of the things that we know, I'm going to draw a prism, is that different frequencies of light have slightly different indices of refraction, or different frequencies of light travel at different speeds in a substance. It's real important. In a vacuum, all frequencies of electromagnetic radiation travel at speed. Radio waves, visible light, X-rays. In a vacuum, they all travel at speed. But in a transparent medium, water, glass, they travel at different speeds. So if I have a prism, y'all know what a prism is. It's a big chunk of triangular-shaped glass. It looks something like that. And if I were to shine white light, and I can't draw white, so I'm going to draw my white light blue. And I have white light coming in. When it enters, those colors separate. And what's going to happen is the red will actually travel the fastest. The red's going to bend, but it's going to be the least affected. The violet slows down the most. It bends more. And what we see coming out of the prism, instead of just white light, is a rainbow of colors. And it will be in the order of the color spectrum. It'll look like a rainbow: red, orange, yellow, green, blue, violet. That's called dispersion. That's spreading out of colors that takes place because of the different speeds that the different colors of light travel. Dispersion is how we explain a rainbow. Rainbows are caused because tiny little water droplets in the sky or in the atmosphere behave like little prisms. So we only can see a rainbow generally either right before or after rain or during the rain. So you have a water droplet. Again, white light is going to shine in this water droplet. But what's going to happen is when this white light enters, it's going to split up and it's going to hit, it's going to refract here, it's going to bounce, it's going to refract out. I may have one too many. And it's going to come out at a certain angle. This may not be drawn perfect. You're going to have to give me a little forgiveness on that. The violet light does the same time, only it splits and it bends and it bends and it comes out at a slightly different angle. Okay, so why do you see a rainbow? Why don't you just see a bunch of dazzling colors every which direction? Well, when you're standing on the ground looking, here you are, you actually only can see one color from each droplet. And all of the droplets at red are going to be at a certain angle. So that certain angle for red may be right here. And you see that red bow. All of those are at the same angle to your eye. And then you see the orange, and then you see the yellow, and then you see the green, and then you see the blue, and then you see the violet. Okay. They're all at slightly different angles. You would actually see a whole cone, because if we draw this kind of sideways, a rainbow is actually almost like, here's your eye, a cone of color. So this could be the red cone. But the problem is the bottom part of the cone gets cut off by the ground. You don't see the full cone. You don't really even see that much. The bottom part, this is so far away that all of this gets cut off by the ground. So you see this rainbow here. The cone for the violet light is smaller. And again, it gets cut off. But whether all the other colors are in between. But a rainbow is basically just the result of tiny water droplets acting like prisms. If you want to make your own rainbow, all you need to do is get a water hose. You feel like you need a little cheering up. Make sure the sun is at your back. Works good in late afternoon, sun's at your back. And you get your water hose and you spray a nice bunch of water droplets up here in front of you, and you can see the rainbow. I see them all the time when I'm out watering my plants. So that color spreading out is called dispersion, and dispersion is responsible for rainbows. Here is an important idea. And I'll be honest, the book goes into much greater depth of the explanation of rainbows. I'm not interested in you having that serious of an understanding. I think it's enough that you understand what a prism does and what dispersion is. And the fact that when you're looking at those water droplets, you see red for droplets that are at a certain angle, and they make that rainbow shape. You see orange for droplets at a certain angle, and that's why you get that bow shape. Total internal reflection. Okay, total internal reflection only happens when light is in a high density material, a slow material, and it's trying to leave into a low density material. So it might happen for light that's in glass that's trying to go into air, or light that's in water that's trying to go into air. So let's draw a picture. Let's let this be water down here, and this be air. Now, if you have a light and you shine it straight up, I think I'll use purple again. Get my markers. if I shine the light straight up, it doesn't reflect or refract at all, just travels straight up. But if I shine it at an angle, remember, if it's going into something less dense, when it refracts, it bends. If I come in at a bigger angle, it may bend until it reaches that 90-degree mark. This point where it reaches this 90-degree mark is called the critical angle. And instead of doing this, it's going to actually bounce back in. And if I come in at an angle that's even smaller, it will all stay inside. Okay. So when light is incident at the critical angle or at an angle bigger than the critical angle, all the light reflects back inside and none of the light can escape. That's total internal reflection. Okay. Has some interesting applications. Okay, let's remember, at angles greater than the critical angle, we get total internal reflection. So for some glasses, types of glass, the critical angle is usually about 41, 42, 43 degrees. So if light is incident at an angle that's bigger than, say, 42 degrees, you get total internal reflection. So let's suppose I have a right triangle prism. Now, a right triangle prism looks like this. I may not draw it perfectly. It's got a right angle here, 45 degrees, 45 degrees. It's a 45, 45, 90 prism. Well, if I send a beam of ray in, light in, just like this, it was a straight beam, that angle with the normal right there is 45 degrees. And the critical angle is 42. So none of the light comes out. Instead, all the light reflects, and it reflects at that same angle, which makes it bump down there. Again, it's going to be incident right at 45 degrees. So it does the same thing again. Now this time when it hits, it's at 90, and it goes straight out. This 45, 45, 90 almost acts like a mirror, because none of the light comes out on this side or this side. It all goes right back through. And they do all kinds of things in telescopes and microscopes. They'll come along and they'll put another one right here. And before you know it, this same beam of light is doing that same trick and being redirected over here somewhere. So they have a lot, this idea of total internal reflection has a big role in things like telescopes, microscopes, binoculars, other types of optical instruments. It's got less useful things too. If any of you ladies own a diamond ring, if you go outside in bright sunshine or go in a jewelry store, they have the best lights, and you look at your ring, it sparkles. You see lots of color. Why? Well, remember I told you, diamonds have the highest index of refraction of most common materials. Light slows down. So one thing that happens is light literally travels slower. But the other thing that happens is it has a really small critical angle. Total internal reflection happens a lot. So if you have a diamond and it looks there, there's your kind of diamond shape. They're really cut to help all this happen a lot. I'm not going to try to say what exactly happens, but you send white light in. It acts like a prism, and instead of just getting white light, now you have red, orange, yellow, green, blue, and violet. But let's just say there's some red light. It comes in, It hits a surface, it can't get out, it bounces. It hits a surface, it can't get out, it bounces. It bounces around and then finally it escapes. So you have all those colors of light being totally internally reflected, bouncing around. And the result is your diamond sparkly. Plain piece of glass that has an index of refraction of around 1.5 or 1.6 has a much larger critical angle. It's going to be more like that 42 degree instead of this diamond with its 24 degree angle. It's not going to be near as sparkly. You're going to see the difference. Now, I'm not saying that's a really important thing. I'm just saying there's a reason that diamonds sparkle and cut glass doesn't. All right, other practical things. Fiber optics. Fiber optic cables use total internal reflection to transmit information long distances. We have fiber optic cables that are underneath the oceans for sharing data. Buildings, when they run computer networks and stuff, they use fiber optic cables. They're so practical, they work so well. They're plastic, they're flexible, you can bend them whichever way you need to go. They cost much less money than, say, copper wiring used to cost. But they work on this principle. Let's suppose this is a fiber optic cable. And they can be all kinds of wiggly shapes. It doesn't matter. You can bend them any way you want to. And you want to send some type of digital signal, which is based on light, an electromagnetic wave of some sort. So you send it in there. Total internal reflection keeps it in there. It bounces, it bounces, it bounces, but it doesn't get out. Until you reach the end. If you've ever had those little toys at the circus that have all the little, they look almost like fishing wire, all those little cables at the end of the flashlight, and you can see all the little beams of light coming out the end of all those little cables, but they don't come out the sides. So fiber optic cables are really important technology that we have. Okay, let's talk about lenses. We're not going to go in great depth on lenses. The book goes into more depth than I want to. They do talk about the idea that you could take a lens and think of it as a lot of little prisms. But I just want you to know there's two basic types. You have lenses that are converging, and you have lenses that are diverging. If you have a converging lens, it always is thicker in the middle. You probably think that that's what a lens should look like. If you take parallel rays of light, and I'll tell you a great source of parallel rays of light, sunshine. The sun is so far away from us that all of the rays of light that reach us from the sun are virtually parallel. So if you went and took this outside and held it outside from the sun, you couldn't really see the rays of light coming in, but you'd have all this sunlight coming in. And what you would notice is they would all be converging to a single point. I didn't draw that great. That point is called the focal point. When you bend rays towards one another, that's called converging. They're getting closer. Okay? The other type of lens is called a diverging lens. A diverging lenses do just the opposite. They tend to spread light apart. Its lens is just single. If I had a diverging lens, it would always be thinner in the middle. And what I would see is if I had those same parallel rays from the sun coming in. So here they are, they're all coming in this way. just like these were. They came in this way. They won't. They'll actually bend out. They spread out. But what happens with them is if you trace them back, they also appear to come from the same point. But over here, it actually looks like those rays are all coming from this focal point. There's not actually light focus there, but the light over here appears to come that way. So one of the places where I feel like you ought to be maybe just a little bit familiar with lenses is this whole concept of eyeglasses. Why are people nearsighted? Why are people farsighted? What kind of glasses do what? Now this is really simplistic, but I put a little slide in there just to show you what happens. If your eyeball is perfectly round, there's all your lens, I don't want to draw all the parts. You will form your images right here on the back of the retina, which is exactly where you want your images to form. So if you're trying to form an image of, say, the sun, they're going to all come in, they're going to bend just the right amount. And that image of that sun is going to be focused right there. Don't look at the sun. It's very, very bad for your eyes. Something else, though. It'll focus more. But if your eyeball is too short, you've got kind of a funny eye. Your image could be back here, but you need it right here on your retina. So we need to diverge those rays. We need to converge those rays sooner. If we want to converge those rays sooner, they're going to put a lens like this in front of your eye to help you converge those rays sooner so that your image is forming right on the retina. When your eye is too short, that's hyperopia. Believe us, is that right? We call hyperopia farsightedness. Now the other possibility is that your eye is long. When your eye is too long, you want the images forming on the retina because that's where your optic nerve is, but you may have a situation where your images are forming up here. Again, here's all the parts. I don't want to draw all the parts of the eye. But you want the images here, but they're forming way... But they're forming up here. So let me get that straight. You want them here. Draw that better. But they're forming here. Well, if they form in front of your eye, what's forming on your retina is actually going to be kind of blurry. We need to spread these rays out so that they don't form an image until they reach your eye. This person is what we call has myopia. You guys think myopia is being short-sighted. So what they do for myopia is they put glasses that look somewhat like this. You've probably seen somebody who the edge of the glasses look really, really thick. Well, the center's probably not that thick, but they have myopia. And so that's going to spread out those rays of light. So instead of forming an image up here, they're going to form the image back here where you want it. So a converging lens will focus those rays a little earlier so we can get it right on the retina. A diverging lens spreads those rays out a little bit so it takes longer and they can reach the back of the eye before they form that image. Okay, I think that's all we're going to say today about reflection and refraction. If you've got questions, shoot me an email or come to a meeting.